This is lab 4. I am joined by my pet Cashew. He will be my identifier for this lab. So going over my Arduino code, I used micros as my delay. So to do that, I set FS, my sampling frequency, to A2. That's just reached from the potentiometer. Calculate the delay, and then I set this variable TI to micros. So that gives me the current time. Now I run this if statement. If the current time minus the initial time is greater than or equal to the delay, then it prints out the analog read, the value of the sine wave from ENSCOPE. And to prove that this works, I'm just going to upload this. I inputted a sine wave, and then I run processing. COM0. So as you can see, it outputs the sine wave in the time domain at the top half, and at the bottom half, it shows the amplitude chart, which is the frequency domain. And at the bottom left, you can see that my sample rate changes, and I can change the sample rate depending on the position of the potentiometer. So I can lower it and increase it. These are the screenshots of the VSA for each frequency. So the sampling frequencies marked in red are the ones that will alias. So starting at a frequency of 75 Hertz, the frequencies that will alias is 142 Hertz and 100 Hertz. For 100 Hertz, the frequencies that will alias, the sampling frequencies that will alias is 142 Hertz and 100 Hertz. For a frequency of 215 Hertz, the frequencies that will alias are the 200 Hertz, 142 Hertz, and a 100 Hertz sampling frequency. For the frequency of 300 Hertz, all sampling frequencies will alias. And those are the reported aliasing frequencies. So these are my calculations using the folding diagram. Calculations for each aliasing frequency is for 500 Hertz signal, or 500 Hertz sampling frequency, 200 Hertz sampling frequency, 142 Hertz, and 100 Hertz. Back to the table. So overall, in summary, the theoretical and experimental aliasing frequencies are very close. It's little to no difference. It's very small difference. So I would say the theoretical frequency is a good estimate. For none, there is a small difference, but it's only by 1 or 2 Hertz, so it's practically none. Use the square wave. It's the ENSCOPE input. And then here's the VSA. Here's the triangle wave in real time. So that's the ENSCOPE input. And that is what the VSA shows. So for the triangle wave, it acts as expected. It will set a frequency of 10 Hertz, so most of the amplitude is concentrated at around 10 Hertz. And there will be no aliasing frequency because we are sampling at a high enough sampling frequency. But for the square wave, even though we were sampling at a high enough frequency, it was still 10 Hertz. Although most of it was concentrated at 10 Hertz, we have additional harmonic frequencies appearing throughout the square wave.